So our next presenter is Dr. Daniel Zablewski, who has over 20 years of experience in materials engineering with emphasis on ferrous and non-ferrous metallurgy, including solidification of cast components. He spent 6 years at the Transportation Technology Center as a metallurgist for the Association of American Railroads, where he directed a rail wear test program for premium, intermediate, and standard rail types. From mid-2015 to present, Daniel has been with the National Research Council Canada Automotive and Surface Transportation as a metallurgist, where he continues to work on rail and wheel metallurgy related projects. Join me in welcoming Daniel. I think you're muted there, Daniel.
Okay, this should be better now. Sorry about that. Yes, thank you very much for this introduction, and I'll just jump right in. So today we'll be looking at the rail failure root cause analysis on a North American railway. So as a background, there's very harsh operating conditions. The harsh environmental operating conditions, they increase the probability of the rail failure. There's two different regimes that cause this to happen. You either have the excessive wear regime or the excessive RCF regime. Either one of those destroys the rail running surface and causes cracks to initiate, propagate, and then lead to the critical failure. And that's obviously detrimental to the rail life cycle. There's ways of preventing those, and we'll address some of those today during the presentation. And one of them is the irregular grinding and the lubrication practices that if not optimized, they reduce the rail life cycle potential. And obviously, the North American winters they offer very harsh operating environments, and they increase the tension in the rail, and that's causing the rails to fail early on in some instances. So, for the purpose of this presentation, we'll be looking at the mechanical properties and the chemistry of a specific rail type, which is the Algoma 115 RE 1985 standard rail grade. We'll look at the analysis of the critical failures that occurred in this rail grade in a 5-degree curve, and then we'll take a look at the track inspection that was carried out in a specific railroad that had that rail grade, that allowed us to sort of make a comprehensive assessment of how that rail behaves in track and what are some of the conditions that might lead to future derailments in the case that this rail would have a similar type of defect that we saw in the analysis and the fractography of the failed rail. And then we'll pinpoint some of the causes of this failure, and we'll look at the recommended practices and how to go about making sure that this failure does not happen. So for the rail surface condition, the rail that we got in the lab was as mentioned previously, an 85 Algoma type of rail. At the time that this rail was installed in track, this was a pretty good grade of rail. It was considered standard rail grade. And obviously, over the last 30 years, the rail technology has progressed to a point where better rails are available right now. They have better microstructures, better mechanical properties, and therefore are more prone to withstanding higher stress levels, which leads to less failures. Nevertheless, at the time when this rail was installed, this was a fairly good rail grade. So over the course of the lifetime of this rail in track, it accumulated 130 mgt of traffic. It had limited amount of grinding. As far as we know, it was ground just once or twice. Last time was in 2005. And as a result, with the accumulation over the last 15 years and no grinding, the result is what you see on the right-hand side. That's the type of plastic wear that exists in a high rail type of this grade when there's no grinding. To add to that, the rails started developing RCF cracks, especially on the gauge face corner of the high rail. So what you're seeing there is the high rail. That's just a picture, on the left-hand side top. That's a picture of the rail as we saw it in track, and then the rail when it was treated with a dye penetrant, which is a process where you spray the rail with a dye penetrant. It seeps into the cracks, and then you bring it out with a developer to show the surface crack morphology much better. And that's what we're seeing here. So we measured those cracks, and they were somewhere between 4 and 5 millimeters in the section that had the type of failure that's being shown here on the right hand side. Looking at the fractography of the surfaces that led to the failures, we saw that there was a slow growth fatigue component, and this is the stuff that's circled with the dotted line. It's slightly bigger than a big size button, and that grew slowly over time. So what happens is, once you get this type of crack and it progresses to a certain size or a certain percentage of the cross section of the entire rail head, the rail head cannot bear the excessive load that's being placed on it, and that added to the notch sensitivity that's happening right at the root tip of that crack, that leads to the brittle failure. So you have a slow growth component, and that's in yellow, and then a fast brittle component that's cracking much quicker. It's almost instantaneous. So obviously, with this type of investigation, the first step is to look at the obvious things like chemistry, the microstructure, and the mechanical properties of the rail itself to find out if there's any smoking gun in those types of things. So we looked at the chemistry, and the assessment of the chemistry showed that there were no deviations between that specific rail grade and the AREMA grade for standard rails. We looked at the microstructure. The microstructure was entirely pellitic, which is the expected outcome from this type of grade. There was some minor ferrite at the grain boundaries, which was totally fine because this was hypoeutectoid rail, slightly hypoeutectoid. The microcleanliness was very good. This rail was free of voids. We didn't see any type of cavities in it. Nothing that showed there was some heterogeneous material present there that was not supposed to be there. And there was very low presence of oxides, which looking at the past results for those generations of the rail types, that's the expected result. The only thing that stood out to us was the tensile results. So looking at the yield strength and the ultimate tensile strength, and looking at the AREMA guidelines for the standard rail, we saw that this rail had much lower yield strength than UTS, and this might lead to a higher tendency towards plastic metal flow. So in a situation where you have a grade that's not ground for the last 15 years and is being operated on at a steady rate, you will have more plastic metal flow, most likely more plastic metal flow that might lead to the development of those types of defects. We also did the fracture toughness testing on it, and that's supposed to and that's supposed to tell you the resistance of this type of rail grade to winter conditions. And this grade, the fracture toughness properties were fine. They were on average what you would see in today's intermediate rail grades and in premium rail grades. So the fracture toughness was not the issue here, but the tensile properties stood out. So we then started looking at what can we do if we go out to track, and what types of curves should we be focusing on to find out how widespread the problem of those types of rail in track is. So we were looking at 140 miles of track. We looked at the curve distribution first. So we saw that the curves range from either tangent rail and then to 1 to 7 degree range for all the curves in this 140 mile territory. Most of the curves were below 1,200 feet in length. Some of them were upwards of 2,600 feet, but those were the seldom cases. Most of them were quite lower. And the posted timetables, train speed for that line was 40 miles an hour, but that's the posted timetable speed. That does not mean this is the speed that the trains go at all the time. and probably in fact they don't, but we went with that number for the assessment of super elevation, and I'll show you those results in a minute. So those were the first thing that we looked at. So before we get into the discussion of super elevations and what we actually found, it's good to just go over some basics, of the super elevation. There's a best case scenario for an even wear and plastic metal flow in the high and low rail, where the life is optimized for both components, for both the low rail and the high rail, and that's the balance speed case scenario. That's where the super elevation difference is 0, and there's equal loading that the rail is being placed on both the high and the low side. In that case, you're supposed to put the even load on both rails. You're wearing them evenly. There's a propensity to develop even RCF on both rails, and it's essentially the best case scenario in terms of keeping the rail both high and low in track for the longest period of time. The problem is this condition only occurs for a very narrow sliver of ranges of operating conditions in track. So think of it like a scale that tips left and right, and this is the center of that scale. You have to be perfectly in line with all the conditions being lined up to keep that balance in check. Most of the time, you either have an overbalanced condition or an underbalanced condition, and either one of them destroys the rail that's where the low is highest. So for example, for the overbalanced condition, you have a cant excess, and you put too much load on the low side of the rail, and therefore you have more plastic flow in that location. You have more damage on the low side. That's the overbalanced. If you have an underbalanced condition, the high rail suffers, and you have a cant deficiency, and the super elevation difference is positive, and then you have more loading on the high side of the rail. So since the breaks happened on the high rail side, we decided to look at the underbalanced condition and to find out what's the cant deficiency in the curves that we had, and then how we can go about inspecting that in track. So if we're dealing with 140 miles of track, it takes a very long time to inspect all that track, in one go. So we decided to just focus on 30 miles of track, and then we went about selecting those 30 miles of track in the way that I will describe right now. We plotted the required super elevation based on the posted timetable speed, and then looked at the difference between the required super elevation and the actual super elevation that was measured with a track car. And on the left hand side, you see this point cloud essentially of the super elevation for the required numbers and for the actual numbers, and it doesn't look like much. But when you organize that information into in the curvature domain, the picture becomes much more clear. And essentially, the idea is that as the curvature starts increasing to a 1 degree, 2 degree, 3 and 4 and so on, that super elevation difference starts getting more and more positive, meaning that the cant deficiency starts getting bigger. The problem here is that yes, the trend is good, but the required numbers don't quite line up with the actual numbers, right? They seem to be sort of the same trend, but they're not exact. So we decided to take a deeper dive into that, and we plotted again the milepost for those super elevation difference between the required and the actual. So taking the required minus the actual, and then seeing what has the cant excess and what has the cant deficiency, meaning more high rail damage and more low rail damage. And for the milepost, again, you see that the difference sort of looks like a point cloud again. But if you organize that by the curvature, the picture becomes much more clear. In fact, if you look at the cant deficiency, so the high rail damage, it has more of a normal distribution with a lot of the positive numbers for the cant deficiency being between 3 and 5 degree ranges. So we thought this was interesting because the derailment that we looked at happened in a 5 degree curve, so around that point right there. So we decided to focus on that, and for our inspection, focus on 3 to 5 degree curves that had the super elevation in the +1 to +2.2 range. And we selected about 30 different curves and inspected them over 2-day visit, and then some of the results from that visit are in the paper, and I'll just show you the highlights of that now. So one of the things that we did during the visit is we had an eddy current with us, and we measured the cracking, the depth of cracks of the rails that are currently in track, and compared those numbers to the rail that actually led to the critical failure. And if you remember, I showed you in the first slide that the rail that's shown here in the image, that's from the critical failure. That crack right there on the gauge face side corner of the high rail, that was between 4 and 5 millimeters in depth. Well, looking at the high rail specifically, between 3 and 5 degree curvature, some of the cracks that we saw in track went up to 5 millimeters, and for the 3 degree, one crack was even 6.1 millimeters. So that's obviously concerning here, that you have a fairly high population of those types of cracks in track right now in that railroad, and this is something that should be looked at. So that analysis that led us to select those curves and then go out and measure the curves that we thought might be the problem size, and then finding out that they actually do have those types of cracks that we saw in the rail that led to the derailment. We thought this was the A to B to C to D. That analysis led us to the solution of identifying those locations that had those types of cracks. So visually, what we saw in track, essentially for a 2.6 degree curve, there was a lot of plastic metal flow in the high rail. So here you see that high rail that has a crack of 5.6 millimeters. The low rail has some damage, but not nearly as extensive as the high rail, because the super elevation is positive, and the high rail suffers in this case. There's a lot of plastic wear, of plastic deformation and wear in that rail, and combine that with lack of grinding, since the last grind cycle here was some 15 years ago. This is the type of damage that you see in that rail. So that new rail comparison to the worn rail, you see that there's a big difference here with a lot of plastic, metal flow and a lot of wear on the gauge face corner with that type of cracking. That's very significant. Shift that over to a 4 degree curve, and this is a typical rail that we saw there. So even more plastic metal flow compared to the 2.6 degree curve. And again, this is the same rail age. This is a 1985 Algoma rail for both of them. So this is the type of rail that you have that is very, very similar to the type of rail that led to the derailment. So I invite you to look at the paper and the results, and there's a lot more detail in that. So in conclusion, we looked at the gauge corner fatigue cracks formed in the high rail that led to the critical failures. Some of the contributing factors that we saw was the low rail tensile properties. So not the low rail as in the position, but just the low tensile properties here. And those are especially the yield and the UTS, which might cause some of the plastic flow to be more prominent in this specific type of rail. There was a lack of regular grinding, and there was inadequate track super elevation, which caused more damage on the high rail. Some of the suggested course of action here would be to simply do more frequent inspections to make sure that the cracks that we saw during the track walk, they don't lead to any type of damage, or if you have a broken rail, replace it. The next best is obviously the rail replacement. This rail is fairly damaged. Grinding will not solve those types of cracks, will not remove them at this point. Then the best course of action would be just to replace that rail with even intermediate hardness rails that have better properties, especially yield and UTS, than that specific rail grade, which the railroad is doing right now, to their credit. The next step would be to modify the super elevation to reduce the high rail loading. This is a bit more problematic because you do need to a very accurate mapping of the train speeds within that subdivision. Meaning that this analysis was done with the posted timetable speeds of the train speeds, which might not be the true train speed. So to get a clearer picture of how the trains are actually traveling through that zone, and then finding out which curves are should have rails replaced first because they're at a higher risk of forming this type of derailment. That type of analysis would be beneficial to make sure that you don't get more derailments. And the next point here under the same heading of modifying super elevation would be to look at the track geometry versus train length. So for example, if you're dealing with very long trains that span multiple curves at the same time, and you're designing the super elevation for all those curves, you will be forced to find a happy medium for all the curves to make sure that the super elevation you select for the different curves matches the train speed, which a train speed will be the same for the long train, but that long train will be going over different curves. So you need to make sure that that super elevation is matched to the current train speed. So this is something that should be looked at. And obviously the adequate gauge face lubrication and top of rail friction modification, that's something that should be looked at. And another suggestion that we gave in the paper would be to look at the wheel populations. During the specific study, we didn't have access to the wheels, but one of the ways to optimize the rail life is to design a wheel profile, a wheel profile and a rail profile that are more of an envelope to each other. So knowing the profile of the wheels will help to design better rail profiles, which will extend the rail life. So I invite you to look at the papers where we talk about those results in more detail. But this was just a highlight. And I would like to thank the participating railroad and Alex Wolf for discussion on super elevation.
Perfect. Thank you, Daniel, for that great presentation.